If you thought the James Webb Space Telescope had already shown us the most breathtaking views of the universe, think again. A new observatory has quietly begun sending back images that are changing the way astronomers see the cosmos. These aren't just sharper photographs of distant galaxies. They reveal enormous structures stretching across the universe, hidden patterns shaped by invisible forces, and clues suggesting that the cosmos is far stranger than we ever imagined. The telescope responsible for these discoveries is Euclid. Its first observations have left scientists both excited and humbled. Many researchers admit they expected impressive images, but not the extraordinary level of detail now appearing in the data. Every new observation seems to expose another layer of the universe that had remained hidden until now. Today, we're going to explore what Euclid has captured, why these first images are being called a major milestone in astronomy, and how they may transform our understanding of dark matter, dark energy, and the large-scale structure of the universe. By the end of this video, you'll see why this mission is only beginning to rewrite the story of the cosmos. Unlike most space telescopes, Euclid was never designed to focus on a single spectacular nebula or zoom in on one distant galaxy. Its purpose is much more ambitious. Rather than studying individual objects, Euclid is surveying the universe on an enormous scale, creating one of the most detailed cosmic maps ever attempted. Launched by the European Space Agency in 2023 and operating near the Sun-Earth L2 point, roughly 1.5 million kilometers from Earth, the telescope has a unique advantage. From this stable location, it can observe huge sections of the sky without interference while maintaining remarkable image quality. Its wide field of view allows it to photograph vast regions of space in a single observation without sacrificing detail. This means scientists can examine individual galaxies while simultaneously studying how millions of galaxies are connected across unimaginable distances. But Euclid isn't simply taking beautiful pictures. Its real mission is to reveal the hidden architecture of the universe. By measuring tiny distortions in the shapes of distant galaxies caused by gravitational lensing, Euclid allows astronomers to trace the distribution of dark matter. Although dark matter cannot be seen directly, its gravity bends the path of light traveling across space. Those tiny distortions become a map of something that has remained invisible throughout the history of astronomy. In a sense, Euclid is showing us the framework upon which the visible universe is built. When the telescope released its first large mosaic of the southern sky, researchers were astonished by the scale of what appeared before them. Hundreds of individual images were combined into one enormous panorama covering an area hundreds of times larger than the full moon. Within that single mosaic lay millions of stars and galaxies. Even more remarkable was the realization that this enormous image represents only a tiny fraction of Euclid's planned survey. The mission has barely begun, yet it is already producing one of the richest astronomical datasets ever collected. Scientists can zoom smoothly from immense galaxy clusters down to individual galaxies while preserving extraordinary detail. The result is far more than a beautiful photograph. It is the foundation of what will become the largest three-dimensional map of the universe ever created. That achievement also carries an uncomfortable reminder. If this breathtaking view represents only a small percentage of the final survey, imagine what remains hidden in the unexplored 99%. One of Euclid's most fascinating early observations focused on the Perseus Cluster, located hundreds of millions of light-years from Earth. This enormous collection of galaxies has been studied for decades, yet Euclid immediately revealed details that had escaped previous observations. Alongside the thousands of known galaxies within the cluster, the telescope identified hundreds of extremely faint dwarf galaxies that had never been recognized before. These tiny galaxies may appear insignificant, but they are among the best natural laboratories for studying dark matter. Because they contain relatively little ordinary matter, their structure is strongly influenced by the invisible mass surrounding them. Every newly discovered dwarf galaxy provides another clue about where dark matter is concentrated and how it shapes the evolution of galaxies. The discovery suggests that the hidden structure of the universe may be even more intricate than astronomers previously believed. Euclid's observations also extend far beyond galaxy clusters. In nearby galaxies, the telescope has identified ancient stars whose chemical composition preserves information from the earliest periods of cosmic history. Within globular clusters, it has resolved faint stars that earlier telescopes could barely distinguish from the crowded background. Even familiar regions such as the Horsehead Nebula have revealed unexpected surprises. Euclid's remarkable sensitivity has helped identify free-floating planetary mass objects drifting through space without orbiting any star, hinting that rogue planets could be far more common than earlier estimates suggested. Together, these discoveries paint a picture of a universe that is constantly evolving. Rather than being orderly and predictable, the cosmos appears dynamic, interconnected, and shaped by powerful forces that remain largely invisible. As scientists continued assembling more of Euclid's observations, one remarkable pattern became impossible to ignore. Galaxies are not scattered randomly across space. Instead, they form an enormous network of filaments stretching across hundreds of millions of light years. These immense strands intersect at dense regions where massive galaxy clusters develop, while enormous empty spaces separate them. For decades, astronomers predicted this cosmic web using computer simulations. Euclid is now allowing them to observe it with unprecedented clarity. The visible galaxies appear to trace pathways created primarily by dark matter, forming an immense structure that extends across the observable universe. Looking at these images, it's difficult not to notice how closely this vast network resembles an intricate web, with galaxies flowing along invisible gravitational highways connecting one region of the cosmos to another. The realization is both beautiful and humbling. Everything we see, every galaxy, every star system, and ultimately every planet, exists within this immense framework, guided by forces we still cannot directly observe. And this is only the beginning of what Euclid is expected to reveal. One of Euclid's greatest strengths is its ability to detect an effect that is almost impossible to notice with the naked eye. As light from distant galaxies travels across billions of light years, it passes through regions filled with enormous concentrations of mass. That gravity bends the light ever so slightly before it reaches us, subtly stretching and distorting the appearance of those galaxies. This phenomenon, known as gravitational lensing, has become one of Euclid's most powerful scientific tools. By measuring these tiny distortions across millions of galaxies, the telescope allows astronomers to build detailed maps of dark matter. Although dark matter remains invisible, its gravitational influence leaves unmistakable fingerprints on the light traveling through the universe. The results are extraordinary. Instead of isolated pockets of hidden mass, Euclid is revealing an immense network spread throughout the cosmos. Massive concentrations of dark matter surround galaxy clusters, connect enormous filaments, and extend across regions where no visible structures exist. What makes this discovery so remarkable is that the dominant form of matter in the universe cannot be seen directly. It emits no light, reflects none, and remains beyond the reach of ordinary telescopes. Yet its gravity governs the motion of galaxies and shapes the largest structures known to exist. For decades, astronomers relied mainly on mathematical models and computer simulations to understand this invisible framework. Euclid is now providing observations detailed enough to compare those predictions with reality on an unprecedented scale. Its reach extends far beyond nearby galaxies. Some of the faintest objects captured in Euclid's first observations are so distant that their light began traveling toward us more than 10 billion years ago. Every image becomes a journey through time. Nearby galaxies appear as they exist today, while the most distant ones reveal the universe during its youth. This unique perspective allows scientists to study how cosmic structure developed across billions of years. By comparing galaxies from different eras, researchers can trace how clusters formed, how galaxies gathered together, and how the influence of dark matter changed over cosmic history. The early results suggest that large-scale structures may have assembled faster than some theoretical models predicted. If future observations confirm this trend, astronomers may need to reconsider important aspects of galaxy formation and the evolution of the universe itself. Perhaps the most astonishing fact is how little of Euclid's mission has been completed. The spectacular images released so far represent only a tiny fraction of the telescope's planned survey. Over the next several years, Euclid will continue scanning the sky, adding billions of galaxies to its growing map and revealing structures on scales never before explored. Every new observation will refine measurements of dark matter, improve our understanding of dark energy, and uncover details hidden within the cosmic web. As the survey expands, researchers expect the telescope to generate one of the largest astronomical datasets ever assembled. That introduces an entirely new challenge. The amount of information being collected is so enormous that traditional methods of analysis are no longer enough. Scientists increasingly rely on advanced algorithms and artificial intelligence to identify patterns that would otherwise remain unnoticed. Rather than examining individual galaxies one by one, researchers can study billions of objects simultaneously, revealing relationships that only emerge across enormous datasets. In many ways, Euclid is transforming astronomy into one of the largest data-driven sciences ever attempted. Another intriguing discovery concerns the enormous regions of space known as cosmic voids. At first glance, these appear almost empty, containing far fewer galaxies than surrounding areas. Yet Euclid's observations show that these voids are not simply blank spaces. Their shapes and boundaries are closely connected to the same gravitational forces responsible for building galaxy clusters.